Here. So we can make a light bulb out of a lot of different things. Measure the spectrum of that compared to daylight. This would be the spectrum of sunlight here. One of the things to notice about the spectrum of sunlight is continuous. You see all the colors of the rainbow here, all the way from red. There are different shades of red, different shades of orange, etc., all the way to violet. So it's what we call a continuous spectrum here. The tungsten lamp, that is our incandescent light bulb, is the same, except you see it's much more intense in the red, orange, and it doesn't have much intensity in the blue, violet region. So it would be like a warmer color than sunlight. Sunlight would be a little cooler color than that. If you look at LEDs, LEDs would be a little cooler in color too. It would be a little whiter. This isn't as white. In an incandescent, it's more red than white. Over here, in an LED, it's very white, but if you take a look at the blue, there's a pretty hefty emission here in the blue. And so some people are concerned about that. So, you know, like gamers and other people, they wear special glasses to block blue. Have you heard of blue blocking glasses? Yeah, to reduce fatigue. Some people say that this blue can cause permanent eye damage in LED screens, LED TVs, LED computer monitors. And so people are investigating this, the adverse effects of the eye. Whereas if you look at tungsten, there's no worries there. Fluorescent doesn't look as continuous. Do you see these peaks here in the fluorescent? And so it's not as continuous. It's still, you got this rainbow, but it's definitely got some valleys, deep valleys here, and some big peaks. And so the color of a fluorescent lamp there is going to look a lot different than the color of an incandescent lamp. All these are white light emitters, but the white light looks quite a bit different depending on the spectrum, the actual spectrum of this. And so I told you about the unusual light patterns. What are the unusual light patterns? The unusual light patterns is this. Based on the physics, you should be able to make a light bulb out of anything with electrons. And so one of the simplest light bulbs we should be able to make is like the sun. You know, what is the sun made of? The sun is made of plasma, but what elements make up the sun mostly? You know the sun is mostly made up of oxygen, carbon, now the sun is mostly made up of hydrogen gas. And the two hydrogens is undergoing nuclear reaction. Nuclear reaction, which is the two hydrogen atoms fuse together to form a helium. People are trying to do this on Earth. They're trying to fuse hydrogens together to form helium and generate energy that way. It's called a fusion reactor. But that's beside the point. The point is, okay, the sun's made up of hydrogen. Okay, we have hydrogen gas on Earth. Let's put hydrogen gas in a tube, and rather than excite it like in the sun, we'll pass an electric current through it, an electric discharge like a lightning bolt through it. Pass an electric current through the hydrogen, that should excite the electrons. As electrons get excited, they should start emitting the rainbow of colors, the continuous spectrum, right? That's what it should do. That's what physics predicted it should do. But that's not what it did. And so let's take a look at what it did here, based on our book. Better slides of this probably. Let me just show you a better slide of this. This is called emission spectrum. this is a spectrometer, and basically it consists of our source, and then a slit to pass only a beam of light like this, otherwise you'd have broad. So the light that comes out of the hydrogen lamp, this is called a hydrogen lamp or hydrogen discharge tube. This is filled with hydrogen gas, and you excite the hydrogen atoms with electric current here. The light that comes out of here passes through a prism, and then it's spread into its components, like infrared, red, orange, yellow, green, blue, indigo, violet, here ultraviolet. And this is what's observed. What's observed is not white light. White light comes from all the colors of the rainbow. What's observed is not a continuous spectrum. A continuous spectrum would have all the colors. What's observed instead is a line spectrum. Like, for example, we only see one color of red light, the color at 656.2 nanometers. The red light at 656.1 nanometers and the 656.3 nanometers isn't present. Totally gone. And then there's no orange, yellow. Then there's some blue-green here, but only one color. And then blue-violet and blue and violet. And so the color, when we add up these colors, it doesn't add up to white light. When you look at the actual discharge, it looks purple. And so the light emanating here looks purple-violet in color. And the question is, why is this? Well, the explanation is this. The explanation is, in the sun, when you excite electrons, you can excite them to any energy you want. And so you could have red at 656.1, or you could have red at 656.2. Is 656.2 higher or lower in energy? 656.2 versus 656.1. And so the energy is going to be directly proportional to the frequency, but it's going to be inversely proportional to the wavelength. So the higher the frequency, the higher the energy. However, the longer the wavelength, or the higher the wavelength, or the greater the distance of the wavelength, the lower the energy. So 656.2 should be lower in energy than 656.3. But 656.1 should be higher in energy than 656.2 nanometers. Well, nonetheless, what we're going is from lower energy to higher energy. If you look at the wavelength's going down, therefore the energy must be going up, so we have violet over here. And basically what this says is this. In the sun, the electrons can be excited to any energy, and they can emit any energy of light. So I can excite it to red, but it doesn't stay excited forever. It drops down and then emits that light. Here, what this is saying is this. The electron cannot be excited here. And so if you shine 656.1, nothing happens. The electron doesn't want it. But when you hit 656.2, then the electron gets excited. But if you shine 656.3, the electron ignores it completely. And so this is very weird, because this is like this. Just imagine this as being kinetic energy. So the electron can move, let's say the electron can move at 656.2 meters per hour. But it cannot move at 656.1 or 656.3. It can only move at 656.2. In fact, it can't even move anywhere until it gets to 486.1. And so this is like driving a car. If you drive a car, can you go any speed you want within the limits of the car? Can you go slow? Can you go fast? Yeah. In the sun, an electron can go any speed it wants. It can go slow, infrared, it can go fast, ultraviolet, right? It can go any speed it wants. In fact, it goes all those speeds, because when we look at the spectrum, it emits everything. But in this lamp, with the hydrogen in this tube, can the electron go any speed it wants? No, it cannot. The electron is restricted to only these four energies. That's it. It cannot have any other energy. And so this is what's weird, because classical physics, which is Newtonian physics, didn't predict this. Newtonian physics predicted a continuous spectrum. We should have gotten white light from this, just like from the sun, but it wasn't. Not only that, this unusual light pattern appeared in many spectra. Spectra is plural, spectrum. And so this is the spectrum for hydrogen. You can see this is what we call a line spectrum. Many colors are forbidden. We call this forbidden energy. Forbidden, forbidden, forbidden. These are allowed, 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 allowed. So only 4 colors are allowed. Everything else is forbidden. If we go to helium, we can look. Actually, no, sorry, not helium. So here's hydrogen, the 4 colors. Here's mercury. Mercury has more allowed, but you can still see there's plenty of forbidden colors in rainbows. Here's neon, plenty of forbidden. And so what causes this? Forbidden and allowed. And so this is what was unusual because classical physics couldn't explain this. And so along came quantum physics. And what quantum physics did was, this is Planck. What Planck proposed is that energy is quantized in the sense that there are going to be forbidden and allowed energies. And if we count for the fact that energy, there are forbidden and allowed energies, then we could better understand this. But how can we better understand this? And so what your book says is that this. What he eventually noticed was he was trying to figure out the math. The energy is proportional to the frequency here, but what he did was he did something else to the mathematics, in which he inserted a positive integer into the math. In other words, he said that as long as the energy is 1, 2, 3 of this, then it's okay. So he has n times the frequency here. It's a little bit more complicated than that. But if we try to go 1.1, 1.2, 1.3, all those are forbidden. And so these are the allowed, 1, 2, 3, and then there's factored into the mathematics here, and then anything in between, forbidden. And so people are trying to understand this. You know, why are there forbidden and why are there allowed? And the mathematics are fine. You know, the mathematics, they came up, although the mathematics could only explain certain things. Mathematics were empirical up to this point. You guys recall empirical formulas? Empirical means just based on observation. And so there was a mathematical equation that came up for the hydrogen atom. The mathematical, do you see that pattern? This pattern of lines here, it's hard to see, sorry, but this pattern of lines can be described by a very simple mathematical equation called the Rydberg equation. That's what we call a law, the Rydberg law. But is the law the ultimate goal of understanding scientific concepts? No, the ultimate goal is a theory. And so, so the first theory that was proposed was Bohr. This is Niels Bohr here. He won the Nobel Prize. But Bohr turned out to be wrong, unfortunately. And so the Bohr theory no longer exists. Bohr theory was replaced with quantum theory. And so why bother even talking about Bohr? Because not everything was abandoned by Bohr. I mean, not abandoned from Bohr theory. One of the things that was retained is this. There are forbidden energies and allowed. So this is what we call continuous. There's a continuum of energies allowed. This is gravitational potential energy. So you can get as high or as low as you want in terms of gravitational potential energy. But the way we have to think about this now is that for an electron in a hydrogen atom, there are forbidden and allowed. And so this first step is allowed. But all these energies between the first step and the second step are forbidden. You know, you can't rest there, you can't stop there. And so the next allowed energy would be 2, 3. So in terms of Planck, this is it. N equals 1 allowed, N equals 2 allowed, N equals 3, N equals 4, N equals 5. But can I have 1.1? let's say I wanted to go 1.1 steps up, forget it. It's forbidden. So is that really a good fundamental description? No, it still doesn't really click, right? So what if they're forbidden and allowed? What causes this to be forbidden? Are there stair steps in an atom? No, there are no stair steps in an atom. And so what causes this is what Bohr thought. Bohr likened those steps to radii. They don't have to be in a plane like this. And so he said the first step would be called the first Bohr orbit. And so this is like the moon or the Earth orbiting the sun, or a satellite orbiting the Earth. Let's call this a satellite orbiting the Earth. And so here we have this satellite orbiting the Earth. Well, we can kick that satellite out farther in space. How far out in space do you have to kick it? You have to kick it to the n equals 2. Can that satellite orbit the Earth between n equals 1 and n equals 2? No, those are called forbidden orbits. And so the next orbit that's allowed is n equals 3, n equals 4, and so on. And so these are the allowed orbits. So this is the way the Bohr was visualizing this, but it doesn't make sense from classical physics. It doesn't make sense from classical physics because of this. The orbit's based on the speed, and the faster you move, the further out it's going to orbit. And so this is like saying this: why is this speed allowed, but all these speeds are forbidden? What's causing all these forbidden speeds? It doesn't make sense. Since that doesn't make sense, Bohr put these as postulates. You know what postulates are? Postulates are taken without proof. There's no proof. It's just taken. And the proof, well, I guess the proof is that it works. You know, it seems to work. But again, it doesn't make sense because the electron should be able to orbit at any speed it wants. If it, you just excite the electron a little bit, it should go a little bit faster. A little bit more, a little bit faster. But no, you have to kick it up a notch. Kick it up a notch. Kick it up a notch. Well, anyway, we'll just take that as postulates. And so this is what it means here. These orbits and the energies associated with these orbits aren't evenly spaced. So for example, the orbits grow bigger. So the first orbit, it's wrong how he drew it, but the first orbit's like this. The next orbit's 4 times bigger. The next orbit's 9 times bigger. The next orbit is 16 times bigger. So it grows exponentially. Whereas the energies don't. The energies kind of compressed. So the energy of the first orbit's here, the energy of the next orbit's here, which is quite a bit higher. And the third orbit, fourth orbit, fifth orbit at the top here. How many orbits are there? There are actually infinite number of orbits. How can that be? I mean, if they're, well, if you count integers, you can count 1 to infinity. And so, anyway, it doesn't go up infinitely. Eventually it stops. It stops about here, and that's n equals infinity. So you have to draw an infinite number of lines from here to here. Is that possible? Well, it's not, but it is. That's what we're going to observe. So the lines are going to get very tightly spaced up here. So tightly spaced, it's going to look like a continuum of energies. But anyway, here we have this. There's going to be a gap. So the electron, if this is an electron, it has to kick up there. You can't kick this up halfway. This is like a step. And so it doesn't interact with any of these colors until you hit this one. This one here. And so what happens here is we excite the electron. We get excited with a wave, or we get excited with something else. We excite the electron up here. The electron doesn't stay excited forever. Eventually the electron is going to drop back down. When it drops back down, it's going to emit that wave of light. And so in this case, we get excited. This turns out to require UV. So we hit this with UV, it jumps up here. Eventually it jumps back down.
Now, energy is conserved, so the amount of energy it causes to excite this is 984. The amount of energy it emits is 984. So energy is neither created nor destroyed. So it absorbs UV, it's going to emit UV of the same energy, same wavelength, same frequency. There's a major problem with Bohr. So Bohr came up with some equations for this, some other stuff, and it worked, but it only worked for species with one electron. If you went on to helium has 2 electrons. It failed, the Bohr theory. And so Bohr couldn't explain, an important part of theory is to predict unseen results, right? One unforeseen result is helium, lithium. In fact, the rest of the periodic table, Bohr theory failed, and therefore Bohr theory was abandoned. However, even though Bohr theory is abandoned, people get it confused all the time. People still talk as if Bohr theory were still valid. And so people still talk in terms of orbits. Bohr orbits. There's no Bohr orbits. This theory has long since been abandoned. And so we don't talk about orbits anymore. So what the Bohr theory was replaced with or modified to is the quantum theory, quantum mechanics. Quantum mechanics, 3 important players in quantum mechanics. Quantum mechanics built on what Bohr did. It retained some things and it abandoned some things. One of the things quantum mechanics retained is the whole idea of forbidden energies and allowed energies. All right, but here are the main players of quantum mechanics. De Broglie said this. Have you ever heard of wave-particle duality? When we think about light, we think about oscillating waves. That's light. But do you ever think about a particle of light? There's a light bulb here. Do you ever visualize particles of light coming from a light bulb? Or just light coming from a light bulb? Just light. In classical physics, the way we visualize light is just light emanating from here. But in quantum physics, the way we visualize light is we visualize light as coming in packets. Those packets aren't really particles because they don't have rest mass, but they're little packets of light hitting us. These little packets of light are called photons. And the energy of those packets of light are given by this equation. The photon is thought of as a particle, although particles should have rest mass. So I'll put it in quotation marks. Particle of light. And the energy of the photon is given by h nu. H is Planck's constant. Planck was that guy who first proposed the quantization or the forbidden and allowed Planck's constant. Nu is the frequency, which is equal to hc over lambda. And so that's one of the developments. But the other development by de Broglie is that electrons. When we think of electrons, do we think of waves or do we think of particles of matter, pieces of matter? When we think of electrons, we think about particles. Right? We don't think about waves. Do you think about waves when you're thinking about electrons oscillating, whatever? No, we don't. But you know what? It turns out that electrons behave like waves and particles. In fact, electrons are basically, let me just tell you the end story. The end story is the electrons behave like nothing you can imagine because they have such bizarre, out of this world behavior. There's nothing in this world that you can compare electrons to. Because on the one hand, electrons are like waves, and then in the next instant, they're like particles, like pellets or whatever else. And so de Broglie won the Nobel Prize in Physics for the wave characteristics of electrons. We call this wave-particle duality. Both light and matter share it. And so not just electrons, but all matter has wave properties too, not just electrons.
Another key player in this is Heisenberg. Let's talk about Heisenberg. Now, unfortunately, they don't have a picture of Heisenberg, but they do talk about Heisenberg. So let me talk about Heisenberg just briefly. Where is it? We'll have to talk about Heisenberg later. It's not quite in there. And then Schrodinger. And so what Schrodinger came up with the equation for quantum mechanics. It's called the Schrodinger equation. And that's incorporating de Broglie and Heisenberg. Heisenberg is very famous. You know what Heisenberg is very famous for? The uncertainty principle, which we'll talk about a lot of. All right, so what I want to do is I want to spend some time talking about quantum. Okay, one of the big differences between quantum and Bohr is that we don't talk in terms of orbits. So when we visualize an atom using Bohr, the Bohr model, we visualize the nucleus. Here's the first orbit, the second orbit, the third orbit. These are the allowed orbits. Any orbit in between is forbidden. Now, if we take the first orbit, that's the first allowed energy, that would be the lowest energy. The higher the orbit, the higher the energy. These orbits are called n equals 1 for the first, all the way up to n equals infinity. The n is what we call the principal quantum number. So n equals 1 is the lowest energy, all the way up. The higher the n, the higher the energy. If we take that first orbit, this is how we visualize that first orbit in terms of quantum mechanics. In terms of quantum mechanics, now this is very confusing because we call this an orbit. Do you know what we call this? An orbital. Now, an orbital is very different than an orbit due to the Heisenberg uncertainty principle. So what the heck are you looking at here? You're looking at the Heisenberg uncertainty principle in action. Imagine this. Imagine that at the center of this is a bird's nest. So we got a bird's nest. We want to be able to pinpoint the position of the bird, around the bird nest. Can you tell me where the bird is going to be 5 minutes from now? That's like the electron. Can you tell me where the electron is going to be 5 minutes from now? You say, if it were orbiting like this, then yeah, it's like a satellite. Can you tell me where the satellite's going to be 5 minutes from now? Yeah, because it's just following the simple path, right? But the Heisenberg uncertainty principle says that, no, it doesn't follow a simple path like that. The Heisenberg uncertainty principle says this. 1 second, the bird's here. So if the bird's here, put a dot. The next second, the bird's here, put a dot there. Next second, the bird's here. Sometimes the bird's way out here, right? But more rarely. And so when you look at the dots, well, the bird seems to hang out by the nest mainly. Does it go very far from the nest? No. Not. But can it go far from the nest? Yeah, it can. Well, that's like the electron. And so what we have here is this. This is called a probability density map. And so if the electron is in the first allowed energy, then the probability density map looks like this. Now let's say you had a high energy bird. If you had a high energy bird, then what do you think? The bird has more energy to travel farther from the nest. And so if you look at, this would be n equals 1. If you go to n equals 2, the probability map looks a lot bigger because if we put the nest in the center, then the bird can easily make it farther from the nest. And so when I look at this is what we call an orbital. An orbital shows us the probability of finding an electron in this cloud, this electron cloud. And this is the allowed energy. And
Now, if I have the next allowed energy, which is going to be higher in energy, the cloud is going to look different. There. Well, what is the next? The next allowed energy is a big jump up. And so the question comes about, why is there a big jump up? And so what did Bohr say? Well, Bohr said, it's just, that's the way it is. If somebody asks, why is it forbidden? Why can't the electron orbit just a little bit farther? Well, it's forbidden. But with quantum mechanics, it makes a lot more sense why the electron cannot orbit just a little bit farther. And that is, if we take into account the wave properties, this is not in your book, but just show it. Have you seen this forbidden and allowed energy in real life? Yes, you have. With a musical instrument. If you have a guitar, you can pluck that string like this, and you'll get this frequency. But with that string, are all frequencies allowed? Can you get all frequencies from that one string guitar? If you had a one string guitar, will you get all frequencies? Like high frequencies, low frequencies? No, you're only going to get one frequency. Actually, you're going to get more than one frequency. It depends on how hard you pluck. Because if you pluck it like this, then it's vibrating like this. But the next allowed frequency is if you pluck it very hard. If you pluck it very hard, then you can get this frequency. This frequency is going to have, this has what we call half a wavelength. You see lambda over 2? This one has 2 half wavelengths here. Here's a half wavelength, here's a half wavelength. Can we fit, let's say, can we fit 1/4 wavelength in here? No, 1/4 wavelength won't fit, because if the string is attached here and here, 1/4 wavelength means the string has to be attached here. It doesn't happen. Can we fit 3/4 of wavelength in here, or 2.5 wavelengths? No, we can't. And so what we see is that the strings of a musical instrument are quantized. This is what we call n equals 1, the first allowed energy. This is what we call n equals 2, the next allowed. But can we have 1.5 or 1.1? No, then we have to jump to n equals 3, and so on, all the way to n equals infinity. These would be the overtones, right? This would be harmonic, this would be the overtone. Those are where we see allowed and forbidden. Now it turns out the electrons are like this. The electrons are like this, wave trapped here. In the sun, the electrons aren't trapped. The sun is so huge, and the electrons are totally free. But when you start to confine the electrons to smaller and smaller volume, what happens is the wave properties become increasingly important. And so, when we're looking at the sun or a piece of metal, we don't worry too much about quantization. Because let's say there's an electron here in the sun, and the sun is huge, and let's say it has a wavelength like this. So in order for this electron, the next allowed energy would be adding a half wavelength to this. And so let's say I had 1 trillion half wavelengths here. What's the next allowed energy? 1 trillion and 1 half wavelength. Is there going to be much energy difference between 1 trillion and 1 trillion and 1 half wavelength in terms of sound or anything else? No. But what happens is if you squeeze down the box, so let's squeeze it down. Now this is a piece of metal. And so in a piece of metal, let's say I had 1 million half wavelengths. The next allowed energy is 1 million and 1. Is there much difference there? No. And if I continue to squeeze it, if I squeeze it down to an atom, the size of an atom, in the size of an atom I might have 2 half wavelengths. Well, what's the next one that's available? 3 half wavelengths. Is there a big gap? A big jump? Yeah, there's a big jump. And so what happens is this. Metals, the electron acts as if all energies are allowed because the energy difference between 1,000,000 and 1,000,001 is negligible. In the sun, these are what we call an electron in a gigantic box. But if the electron gets confined in a smaller and smaller box, then we're going to see the quantized energy levels, which we don't notice here. We don't notice the quantized energy levels there. And so what does this look like? Let me show you what this looks like on YouTube. Are we? Okay. Sorry. We're down then. All right, I'll show you what this looks like tomorrow.